So I come from a company called AID, and we are based in Munich. It's a 100% subsidiary of Audi. This means that we would develop the autonomous driving for the entire Volkswagen group. It's what we do is actually we do level 4 and level 5 autonomous driving, and yeah. As I said, the company is based in Munich. We have several working prototypes, and unlike my previous speaker, we don't need to chase fog, so fog chases us, and so does rain and snow and everything. It's a fairly young company and startup-like atmosphere, and with very professional and humble people all over the world. Yeah. And it's a sponsor for an event which is called Formula Student. So what is Formula Student? It's a worldwide event, which is basically it's held all around the globe, with Germany being the known, like the most known competition. Teams from university all around the world build full-size race cars. That means that they do everything from the engine, aerodynamics, suspension, and cost analysis and business model. And actually, since 2017, the German competition introduced a new class of driverless car, which followed by all other competitions, or all other major competitions. So how are the teams are being evaluated? There are two events. There is the static events and there is the dynamic events. In the static events, the teams present their work. They are scored according to the business plan and the cost analysis, and most importantly, the engineering design. This is where we come in a minute. And the other event is the fun part, which is actually the car gets to drive on the tracks. There are three different tracks. There is acceleration, skid pad, autocross, and endurance. So what exactly we need to do in this event? Basically, it's a simplified driverless problem. You need to just stay in lane. That sounds fairly simple. On top of that, to make things easier, the tracks are marked with blue and yellow cones. And in some cases, the track is already known. You get to drive on the track, and then you get to record it. And then when you drive it again, you get to use whatever you know about the track. So it sounds kind of a simplified task, and it is, but then again, you can see that a lot of teams find it hard to handle. There's one thing I forgot to mention. Actually, there are two teams that are competing from Israel. One is from the Technion and another one from Be'er Sheva. And yeah, it's really interesting. So how do you design the self-driving stack architecture for this simplified problem? So basically, we first have the sensors that acquire the data from the surrounding car, and then they pass it to the perception pipeline to detect or to estimate the position of the cones, the position and the color. This estimation is going to the localization and mapping algorithm that utilize the cone locations in order to build or use some kind of a map and build some kind of a map. This map is then, a path is being generated using this map, which using the control according to the vehicle dynamics and the physical constraint of the system. And then it's passed to the actuators, control the throttle, the brakes, and the steering. This is, in order to actually to design this kind of pipeline, you need to take into consideration that all the needs of the system and all the requirements from the actual from the competition. For example, the location of the sensors should be coupled with the required detection distance from the planner and the number of possible outliers for the SLAM algorithm. On top of that, GPU ratings should be matching the allowed power consumption and weight and limitations of the car. From this point, I will talk a little bit about the sensor and actually about the perception for this case. So what kind of sensors can we use in the car? We divide it basically into 2 or 3 groups. There is the vision sensors, which provides very rich information about the scene, but then needs to be evaluated in a more complicated manner. There is the LiDAR, there is the active distance measurement devices, which provide sparse dense information, and there's a group of all other devices. And when we talk about each one of the devices, again, we need to understand that whatever we choose has an effect on the rest of the system. For example, choosing a 4K camera makes little sense if it's going to run through a detection network that yields a low frame rate when a higher frame rate is needed for the SLAM algorithm. All those camera parameters should be coupled with other components in the perception pipeline. Regarding stereo images, stereo cameras, so there are many commodity stereo cameras available in the market with camera mounted on a rigid jig and an API to access and calculate the depth and even to perform offline calibration for those cameras. The problem that most stereo algorithms are being run on the host computer, which consumes the processing resources. There are some exceptions, like the Intel RealSense stereo cameras, which are doing the stereo matching on the device, but still stereo in general suffers from a quadratic depth error, which is actually inferior to other depth measurement devices like LiDARs. And I will talk, well, basically, although solid-state LiDARs are currently starting to appear here and there, they are expensive and not yet mature, and I don't think that they are appropriate to this task. And like rotary LiDArs that have been around the market for at least a decade. So most products that are available are the same. A set of emitting devices are set on a rotating platform, and the depth is estimated by measuring the direct time of flight. This means that you transmit a pulse, receive it, and measure the time difference. The vertical accuracy is quite limited compared to stereo, but it should be sufficient. But it really outperforms in terms of range and accuracy. And as I said, there are a group of other devices. The most commonly known are IMU, Wheeltix, and GPS, which are very easy to interface and use. These devices are great to get an initial guess for methods that require a good initialization. But the uncertainty of those devices are generally insufficient, and you cannot use this data directly. So what are we going to do with all this data? So let's say we actually designed the car, and like this is one of the proposed designs. And we found a way to, and we decided on a place to place our cameras and LiDARs, and we have a certain location, which is called the ego vehicle, which we would like to transform all the coordinate systems into. So currently, each one of the devices is operating on its own coordinates frame. And in order to use the data from all those devices, we need to bring them to one common coordinate system, which, as I said, we call the ego coordinate system. This process is called sensor calibration. And in the sensor calibration is actually a process that we estimate the set of parameters for each one of the sensors. We would like to find the transformation, the translation and rotation of each of them. And of course, if exists an intrinsic and internal set of parameters, for example, for cameras. And in addition to that, we would like to time synchronize them, that first of all, the temporal region of interest would be greater, so that we'll get a nice temporal coverage. And in addition, they would not interfere to one another. For example, if you have a camera with no IR cut, this means that the LiDAR would be visible in the camera, which would create artifacts. So you need to mitigate this one as well. And so at this point, so we have a set of sensors, and we would like to find the calibration between them. So when getting the design from the mechanical team, we know generally where they are placed in the car coordinate system. But then again, if we have more than one camera, and we can do stereo matching between them, we can get the transformation between each one of the cameras. And if we have one LiDAR, then we can get the relative position between them by performing ICP. And if we do that, and we know that we are in a very specified scene, so we can actually find the transformation to this scene both from the LiDARs and from the cameras. And again, if we have, for example, a GPS device, and we know how to find the transformation from the car to this environment. In other words, we have some kind of transformation graph that we would like to solve, and we would like to find the set of parameters that minimizes the edges on this graph. So this problem was already addressed in the past, luckily. And actually, if we have a good initial guess of the set of parameters, numerical solution of the equation over here can be obtained by popular Gauss-Newton or Leavenworth Markov algorithms. Then the problem with these algorithms that they assume that the space of the x parameters is Euclidean, which is not necessarily true for SLAM or bundle adjustment, where there are some parameters that, for example, the angle span over the rotation group, the 2D or 3D rotation group, and it's not very suitable. And but this could be overcome by expressing the increments of this delta x in different space from the one of the parameters, or computing a new arrow function and calculating the perturbation around the delta x. The general framework that was proposed by this paper, which is called G2O, is open source, real-time optimizer that solves the calibration pose graph and actually other problems, like the one that is demonstrated here in a paper from 2015, which is called Robust Reconstruction of Window Scene, and you can see that it really performs a really good and really accurate reconstruction. So let's say that we've solved our calibration issue, so we have LiDAR and cameras, and we would like to see what we can do with them, whether mutually or individually. So if we look at the LiDAR and we're looking at the recognition problem, which is basically analyzing the data from the LiDAR, which is, we can call it clustering, 3D bounding boxing, or segmentation, etc. And we would like to see what can we do only with the LiDAR data. So something that could be found extremely beneficial is to cluster points that belongs to the ground surface. Now, once this is removed, actually detecting obstacles is quite straightforward. The problem is that the floor is usually not flat, and trying to fit a single plane to the entire point cloud would fail. More complex and something more complex is required. This paper by Frank Mussmann, the points are clustered according to some local convexity that we can assume that between 2 points we have a certain angle if we know the points and we know the normals. So we would like to connect 2 points that has some kind of connectivity threshold and create some kind of patches. Now, after we patch the entire, after we run this clustering algorithm on the entire point cloud, we can find which one of the clusters belong to the ground floor and can easily cluster it out. Another thing that we can do with LiDARs is actually odometry and localization. Again, this is a paper from 2014. The key idea behind this, again, real-time and open source implementation is to divide the SLAM problem into two different algorithms. One performs odometry at high frequency, but very low fidelity. And the other algorithms run at an order of magnitude slower, but do a fine matching and registration for the point cloud. Together, both of them achieve real-time performances, and as I said, this is open source, and you can download it and easily integrate it. There's another paper that is worth mentioning, which is the Google Cartographer, but it's most suited for indoor scenes, but it works fairly well on outdoor scenes as well. So this is one thing. I would try to keep it short. This is one of the processing pipeline, and another one is the same pipeline with the cameras only. So what we can do with the cameras, again, is pretty straightforward. We would like to find, first of all, cones. So finding cones in the image can be done basically by template matching, but if you want something more complex, you would like to learn the template that you're using. But why not using something that, again, that is off the shelf? So what is usually being used is the You Only Look Once paper from 2016. And if you don't know this paper, it's quite interesting. It's unlike to previous work that that work that repurpose classifiers to purport detection. This paper, they propose a single neural network that predicts bounding boxes and class probabilities directly from the images in one evaluation. Now, since the whole detection pipeline is a single network, it can be optimized end-to-end directly on the detector performances. In order to train this network, so we need data, and the teams from Formula students created some kind of database, and they are working on it. And this is how you can actually train your network specifically for this task. Now, in order to create an individual pipeline for this task, so once you have the detection of the cones in 2D, going to 3D is again quite straightforward, because each detection on the camera plane can be easily transformed into array. And if you have a good camera calibration, you know where your camera sits on the car. So actually you know where the ground plane is, because we evaluated it before. And by looking at the intersection between the camera ray and the ground plane, you can get the exact location of the cone in the car with very little effort. Another thing that we can do with camera that is worth mentioning is camera odometry. And for the people that were here this morning, I think they already heard that talk. And basically what the group from TUM proposed here, that to accurately reconstruct the camera ego motion and the surrounding geometry. Now, unlike feature-based method, they rely on feature extraction and matching. In this paper, the authors directly operate on image intensities, both for tracking and mapping, and they are taking into consideration real-time artifacts like exposure time, lens vignetting, and nonlinear response function. And again, they perform in real time and in high accuracy. Yeah, all right. So what do we do with those two things? So we have two individual pipelines that are working in parallel, and each one of them produce different results. So at this point, we need some kind of a fusion mechanism to join those two detections together. Now, the problem in here is that you can get two different observations of the same thing, and you need to join them together. And this, this method is more prone to error, because again, you have two different modalities looking at the same thing, and then at the end, you join them. But a more robust way would be to make the the fusion, making a low-level fusion, and creating some kind of an RGB XYZ image and working on it. The downside of this method is that it requires a very good initial calibration. And not only it requires a very good initial calibration, but on top of that, in case that one of the sensors fails, then you need to fall back to the other methods. But working on a joint method would be much more robust and much more prone to failure. Yeah. So in general, we just got a high-level overview of the design of a self-driving pipeline specifically for Formula race cars. The constraint of the design arises from the competition requirements and actually from the actual car performances and the compromise between them and the actual available hardware. All the papers that I've showed here are open sourced and can be easily integrated using ROS and connected together like building blocks. And, but you need to bear in mind that you need to carefully consider the inputs and the output requirements, but then again, you can create a robust, fast, and reliable perception system. Yeah. And thank you.